Very good. Is that working? Okay, thank you. Right, so I want to say a bit about how you actually, or how I actually get these shells that I was showing you, and what lessons there are to be learned from the evolution from flat space to follow a curved metric, and how indeed the details of the shape evolve. And I've already said yesterday a bit about why one wants to do this, and I mentioned also these very fine collaborators whose work I'm going to talk about. So this is the why. You remember we want to get away from just flat space, and resisting the development of Gaussian curvature means that things are very strong, and we thereby want to get to slender but strong lifters, as I was saying a couple of days ago. So, and this is my friend Tim White. He can take these sheets and print something which changes the metric when he heats it up, and it turns into an array of square pyramids which act as lifters and are very effective, as I showed you, lifting several thousand times their own weight. So to get there, we need reversible shape-changing materials, and they should be imprintable so we can record what metric we want to evolve to, and they should be steerable, and light is the best one, I think, at heat as well. And then I reviewed a bit about how these things change shape by extending or contracting, by lambda, contracting in this case, along the director, and by lambda perpendicular to the director. And I gave some examples which go from, say, 10% to 400% length changes when we shine light on these objects. And they have a Poisson ratio, an optothermal one, which says how they react in the perpendicular direction, shrink by lambda, they expand by a factor of lambda to the minus nu. And there's a range of values of that. And the bottom line was a deformation gradient tensor, which is here, and it's encoded the magnitudes by how much it extends or contracts, and the direction, the director along which this contraction will take place. So this is the sort of master deformation gradient, and we want to get topography by looking at a variation of the spontaneous deformation lambda in specific directions, and we'll do it via a spatial variation of the director. So at a given temperature or light level, there will be a changing, a given value of lambda, and we can change that by illumination, but we'll vary spatially purely through the direction at which the director points in the plane. Now, following me, there'll be a much more sophisticated talk about varying it in other ways, and you will hear about that, I hope, rather shortly. So I should emphasize the work of Aharoni and various other notable people. They, way back, used Cartesian patterns of the director distribution. They also looked at the inverse problem, going from a if I tell you what shape I want, you can go backwards, get the director distribution, and then variation through thickness to control the curvatures. Yes. 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 Yeah, and I won't do that. But yeah, you could vary the lambda from position to position, because the extent to which it will extend will depend on how tightly cross-linked it is. I won't do that. But yeah, there are lots of degrees of freedom. But we'll hear much more about that shortly. This work lived upon other work about managing the metric, but not by direct, liquid crystal methods, but by swelling and so on. And then some work that I've done with a very able man, Cyrus, here. So we talked all the time really now about the fact that the squares of the distances in the space we're interested in can be related to the squares of the distances in a basis state, which is a flat space, and a metric tensor connects the two. And by folding this, these two expressions together on each side, this combination of the deformation gradient gives me the metric tensor. And that's the metric tensor of this new state. Once I've shone light on it, it's got a natural shape. and it's a square of this, this object here, and it's an easy object to square, so I write that down there, and this is the thing that you should keep in mind. So the metric tensor, there's a natural lambda squared minus the perpendicular one along the director, and then in all the other directions, lambda to the minus 2 nu. It just says lambda squared along n, lambda to the minus 2 nu in the other two directions. And the spatial variation will come through this. Okay, so I want to give you first an example of how we might do that. And so we take a director, and I'm going to take circularly symmetric ones, so they'll all be spirals of some sort. And this is the initial director here, this heavy red line. And the director makes an angle alpha, which is a function of position out from the center. So this alpha is a function of r. So that's my initial pattern. That's the one that Tim White writes into these objects. And then we're going to see what happens when we change the lambda by heating, for instance. So the director spirals go from being this red one into some deformed, in the new body is written here, and these are immaterial. So I'm representing them as if they're on this flat diagram, but of course they're on the surface of something that's changed. The circles here, here's a circle, and it deforms into this circle here. And then a given spatial trajectory, which I've called gamma 2 here, it will deform into a radius immaterial afterwards. So I call this a proto-radius. This is the shape, or this is the trajectory that will deform into a radius. And I have to keep track of those because my grand scheme is to try and reconstruct the surface that this is going to make. And of course, as we know, the metric doesn't define the surface, and you have to do some work to get it. And in general, you can't, but I'm taking surfaces of revolution, so it allows me to solve this problem. So remember these proto-radii, they'll be very important. And it'll be useful to have the metric tensor in circular coordinates, and so this is it. It's got components r, r theta, and theta r, and a theta theta. This is a especially useful one, and it's very simple to write down. And the spatial dependence of the metric comes from the spatial dependence of the angle alpha that the director makes with the radius vector. Oops. So the Gaussian curvature you can calculate from this easily enough, and it's just given by this formula here. So it depends on the variation of alpha with r. I don't know what this extra r is. Oh yes, here it is. 3 over r comes in, and alpha prime squared here. So alpha prime is just the variation of director angle as I go out along a radius. And it's this that leads to the surface curvature. So this is a useful formula in some ways, but it doesn't take us very far. Right. So the challenges are, the forward challenge is, given an alpha of r, what is the shell shape? And the inverse is, given a shell shape and a particular lambda, how much you've heated it by, what is the director distribution I need to get it? And as I said, the metric tensor in itself is just not going to tell you the surface. There's also some serious questions which you must address, but I won't in this lecture, which is about, are these embeddable? Are they still circularly symmetric? And I'll say a few words about anchoring. So if you've got a shell, for it to be useful, you really want to anchor it to an inert substrate so that it remains attached and mechanically compatible on the ring which supports it. And I'll say a bit about that afterwards. So the cone is the simplest one, and we talked about that. It's got Gaussian curvature everywhere except at a tip, and it's got a certain amount at the tip, and you need a constant director angle with respect to the radius in order to get a cone. And that was the simplest case that we started off looking at. And here is the same diagram, but this case, alpha does not vary with radius. It's a constant. And so everywhere, the the metric will be the same, and I will get the same sorts of inflation. So if this angle is a constant, this red line is a logarithmic spiral. So that's the simplest case I can take, a logarithmic spiral, and it will evolve into some curve which turns out to be a logarithmic spiral, and the proto-radii here, they will turn out to be logarithmic spirals as well, all different ones. Do you have a question? No. Okay, so this is the simplest one. Yes? Well, you would see it, for instance, in this expression here, where alpha primed is 0 everywhere. So the Gaussian curvature is 0. But well, right. Well, let me address that very problem. Let me address it. Oh, and look, there's an important bottom line here. Geodesics don't remain geodesics, and that was my criticism of my own demonstration with this little cardboard disc. Yes. Yeah. Okay. So this is the answer in a simple case, namely the constant angle is 90 degrees. And that's the one we saw before. And that's simple because radii remain radii and circles remain circles. So that's preserved, and I just have to go through a little bit of algebra because this circle it contracts by a factor of lambda, and this radius extends by a factor of lambda to the minus nu. And so I can say that that's the new length here. This is the new circumference that's generated by this new in-space radius. And the ratio of those two gives me sine phi. Yeah, yeah. Right. So, but no, it's an important question. So this is a simple case, and then in general, I have to solve this case. Where circles inflate or deflate. So, for instance, this circle, this perimeter here extends by or contracts by a factor of root a theta theta. And I then can construct the cones in exactly the same way, but the relevant lengths are the length of the circumference, which tells me the length of the arm that sweeps out that circumference, and it will be the length of the proto-radius, the length the proto-radius deforms into. So let me try and do that explicitly. So here's a theta theta, reminding you of that. So I need the square root of that to get the new circumference of the circle, and I just simplify the appearance here. I'm taking the square root of that, take out this factor of lambda to the minus 2 nu, becomes that, and what's left behind is 1 minus beta sine squared alpha. So the former circle deforms into the new circle, and this is its change in length. Everything else rotates and distorts, and this is the proto-radius, and the director field rotates and distorts. And now I have to actually calculate, in this particular case, it's a cone. So the proto-radius, well, what I do know about the proto-radius is that when it deforms and becomes a radius, it's perpendicular to the new circle. And circles transform into circles, and you can either prove that or accept it by symmetry, that there's nothing else a circle could deform into. It inflates or deflates, and the material points rotate. So I know that the proto-radius deforms to a new, a real radius, which is perpendicular to the new circle. So if I've got curves, these curves gamma, there's some r of t and theta of t, and I'll take this to be a unit tangent, so it's a unit speed characterization. And what I'm going to say is that these tangents deform under this lambda in this particular way. So I've got lambda the new tangent is lambda dotted into the initial tangent. So I want those to be perpendicular. So this is the deformation of the circle, and this is the deformation transposed of the protoradius. And so I can turn that, expand that together. That's the metric. And so I've got to say that the new radius is perpendicular naturally to the deformed protoradius is perpendicular to the deformed circle. Now the circle is simple. It's just 0, 1, because the radius is constant and the angle evolves at unit speed. So I can put that in there, and I've got a simple expression for the protoradius. And I can divide this by this, and I've got an expression for the protoradius, which is just the ratio of these two elements of the metric tensor. So I can write that down straight away. That's this. And I can integrate this trivially if alpha is a constant and it's just a logarithmic spiral. Right, so the protoradius, which becomes the radius, is a logarithmic spiral initially. It evolves into a real radial vector. So now I want to specify the surface. And the surface, well, let me define the surface by an in-space radius gamma 1 and a height function gamma 2. So this point here is the point gamma 1, gamma 2. It's a surface of revolution. And I've got a distance u, which would parameterize the surface if I was doing it parametrically. So that's an immaterial radial coordinate. I don't know what it is, but I don't know how to get it yet, but that's what it is. So the challenge is I want to describe the surface, which is given in terms of some either parametric representation or just these functions of each other. And I know that the reference state is actually defined by position radius in the reference state and the angle of the director in the reference state. So I have to get from one to the other. So I have to know what is the connection between radial positions in the reference state or the basis state and this length in material in the current state. So let me solve for that. The increment in distance in the shell is just the increment in the along the transform tangent vector times the incremental change in the parameterization. And I can analyze this by using my result for the protoradius, which tells me how these two depend on each other. So if I put that into here, in taking out a factor of dt and shifting over the dr2 here and putting in the determinant of the metric tensor. Yes? And that won't always be true. That won't always be true. There will be cases where it has to start ruffling. Yes, no, absolutely. And there will be then tests for whether that fails afterwards. And then I have to give up. This tells me the connection between the distance along the radius of this circularly symmetric shell and how far out I am on the protoradius. So it connects the two spaces. And the connection is very simple. And it's just this. So there's a connection between U and R2, which is given by this. So I've got that, and so now I can actually write down what the surfaces are. So I can get, first of all, this perimeter. That's trivial. It says that 2 pi r becomes gamma 1 times 2 pi r, but I know that 2 pi r just inflates by that element of the metric tensor, the theta element, or the square root of it. And this radius gamma 1 is what sweeps out that distance there. So I could say that gamma 1, which is a function of u, from the surface parameterization, is just some function g1 of r, because it's ultimately a function of r. since I know the connection between U and R, and it's just equal to root A theta theta. And I know what root A theta theta is. It's just one of the elements of the metric tensor. I put that in, and so I've got gamma 1 as a function of R. Gamma 1 lives on this space, which is defined by U, but I've mapped between the two. And then I'm going to assume that the surface is smooth, and therefore d gamma 2 by du is just equal to the square root of 1 minus d gamma 1 by du squared. Transform that to R, and now I've got the other function g2, which defines this surface. So I've got the height function now in this form, and that's a simple integration mostly, and I've got the other height function in terms of R as well. So everything is related back to the basis state and defines this new shell. So I've now solved this problem in some formal sense, and so these are the solutions which are cones for logarithmic spirals, and I showed you this before, and this is where I definitely am not circularly symmetric, and that I'm not saying anything about that in this lecture. And here, if I have a linear variation of director with radial position, then which is what this is, then I can get the Gaussian curvature simply enough, and then I have this shell that I've calculated the shape of. And at this point, I start worrying about Sabetta's question last time, and I'd still like to talk about that. There are regions of Gaussian curvature here, and how strong these are as lifters, I think, was thrown into question. Anyhow, so that remains, I think, a valuable and interesting thing to think about. And here's a quadratic variation, and again, I think if you look at these, you'd be hard-pressed to tell by eye that they're different, but they are different, and the shells are different as well. And here's an exponential variation, and again, they're different, and you get a particular shell from this. Now, there are limits to how far out you can go and what the initial angle alpha must be at the origin, and if you get that wrong, these are no longer circularly symmetric, or they can't be embedded, and so there are limits here which I'm not going to speak about, but they sit behind all of this. So let's think about the inverse problem. The inverse problem, well, the simplest one is where I actually know the shape. I say I want a spherical cap, or I want a pseudosphere, or something like that. Then I know that this is a constant here, and it's on the left-hand side, this constant. So this is just an ODE for alpha of R. And so I can solve that. So for instance, if K is a constant, then this is the solution of this ODE with boundary conditions, this one including where I've excised the center of the disk. So I've solved the inverse problem here in some trivial sense, in that I've taken trivial shapes with constant Gaussian curvature. I know what they are. They're spherical spindles, spherical caps, and pseudospheres. And this is the director variation that generates that. So that's a solution, if you like. And here is this function plotted that I just showed you, and it generates a spherical cap and a spherical spindle. And I haven't pictured the pseudospheres. This one here. Oh, by very, very tightly, I mean, this one is gone because it's divergent, and we haven't cut the middle out, and then by very tight prescriptions of what these constants can be. And for one case, for a given lambda, you will have a spherical cap, and in general, everything else is a spherical spindle, which is pointy. Yeah, yeah. So, yeah, it's an important point. When you write this pattern, for this to be a spherical cap, this pattern has got lambda encoded in it. And it will only be a spherical cap at that particular lambda. And all the way to that particular lambda, as you're heating or shining light on it, it will be pointy. So it will go via a sequence of spherical spindles until it's a spherical cap. And here's Tim White producing a spherical spindle with a little pointy bit there. Of course, blunted eventually by the fact that this is a finite thickness, and you don't want to make it infinitely pointy if it's got finite thickness. Right, so the inverse problem number 2, which spiral gives the desired shell? And in general, that's quite a difficult problem, and it involves a nonlinear integral equation. But there are some ones. How am I doing for time? Oh, no, I don't need that long. Hope not. So the problem is I have some gamma 2 of gamma 1, which is my shell of revolution. What is the alpha of r at a given lambda? So we get back to actually Jonathan's point. We'll come back to bite us. And generally, it's a nonlinear integral equation. But let me look at shells, for instance, trivial shells, which can be written u is some function of gamma 1. And example of that's paraboloid, for instance. So I can take du by dr, which is d gamma 1 by dr, df by d gamma 1. Now, I know what this is. That's that connection here. And I know what the connection between du by dr from my thinking about the proto-radii. So I know everything about this equation. And I can take an example where, for instance, a paraboloid, which is written like this, then it's easy to show that df by d gamma 1 for a paraboloid is just this, where f, you recall, was what connects gamma 1 to the parametric parameter. So df by d gamma 1 is just root of 1 plus k squared e theta theta, because gamma 1 is just root a theta theta. So, and I know what a theta theta is in terms of alpha, and so this is a differential equation or this will be a differential equation for alpha. So I can solve that for a paraboloid, and the answer is this. Sine squared alpha at a particular lambda is this. So when the lambda reaches the lambda that defines this formula, then I will have a paraboloid. So here's a picture for a particular lambda of 0.8, particular nu, and for that particular lambda, this director field has to have this particular form, which is given by this equation. And so as I start heating or applying light to the system, it will start getting pointy, and there will be a shell that I can calculate by the first part of the lecture. And then eventually, when I reach the lambda that defines this formula, then it will be flat at the top and not pointy, and it will be a paraboloid. So that's I think, a complete solution to this problem. And there's a whole family of curves you can do which have this particular form. The rest you have to work harder for. So this is a summary of what I've said. I want topography from flat sheets of programmed liquid crystal solids. I want the Gaussian curvature. I said before why I want it, all of these things here. It comes from the spatial variation of the metric tensor. There's a forward and a backward problem. And then having done all of this, I'd like to anchor these shells at specific radii. And that's easily done because I would then say the gamma 1 that defines the shell has to actually be the same radius as the one that it maps back to. And that's a statement here. And that is solvable by going out to a radius for a given lambda which satisfies this equation for a given alpha of r. So I can anchor these shells. The anchoring won't be strain-free until I reach the particular lambda for the radius that I've set. And so it will be stressed, stressed, stressed. It will pop up as an anchored shell and hopefully do some useful work. So we'll have not only anchorability but also snapping structure. And with that, I'd like to thank you for your attention.